Le luci, per favore. Presenta Alan Smith, la presentazione è H2 Pod Localized Hydrogen Generation Off-Grid, H2 Pod. Sarà in inglese, naturalmente, in English.
Yes, I'm afraid it's in English, but buongiorno. Bonjour. It's on? Okay. Fine, yes. Okay.
Può spegnere le luci in sala, per favore? Grazie.
Hydrogen is a very fashionable topic at the moment. The European governments are subsidizing hydrogen in Germany, in France, in Italy, because they're trying to build a hydrogen economy. But before I get into that, I'd like to just say something. People talk about green hydrogen, blue hydrogen, grey hydrogen, black hydrogen. We all know hydrogen has no colour. The terms are related to how it's produced. Green hydrogen, which is what I'm talking about today, is made from either renewables or in some sustainable way. Blue hydrogen, which is 95% of the hydrogen produced in the world at the moment, is made from methane gas by steam reforming. And it's not a particularly clean process, but I'm getting off track. So we're building a new hydrogen economy in Europe, but to me it looks dangerously like the old hydrogen economy, or the old normal economy, in the fact that the same companies, the gas companies, the oil companies, the electricity companies, are trying now to build vertical systems where they own both the means of production and the gas and the equipment that produces it. I was talking to a guy from Iberdrola, a big Spanish company, energy company, particularly in electricity. And Iberdrola said to me, they are only interested in vertical models because they want to sell their product. They want to sell electricity. And green hydrogen in Europe at the moment means hydrogen made from the electrolysis of water. And this is only green if it's made using renewable electricity, electricity from solar, from wind, and so on. At the moment, it's not really so. So there is a problem. We're building a new hydrogen economy, but it's the same old chicken, but it's got different sauce. That's all. So I was looking into the problems of this, particularly because a friend of mine in England is an expert on the electricity grid. And he pointed out to me the problems both with hydrogen as a fuel source and with batteries for vehicles, electric vehicles. This hotel, for example, has got something like 100 car parking spaces. If all of those cars had batteries, then they would require quite a lot of charging points for the cars. Each one of those will be maybe 12.5 kilowatts to supply electricity to recharge 100 cars. This hotel would need 1.5 megawatts, which is not necessarily available on the grid. And the same is true of electrolyzers in many places. That I've been talking also with a company in Bristol who collect the garbage. They are the éboueurs, as they say in France, yeah? They collect all the domestic garbage in Bristol. And they would want to change to hydrogen. Their diesel bill is phenomenal. Garbage trucks only do around about 5 kilometers, 1 kilometer on a litre of diesel, because it's all slow speed, low gear, and lots of stopping and starting and stopping and starting. So they decided they would like to buy from Hyundai, who are actually manufacturing them, hydrogen trucks. But they would need a 2 megawatt electrolyzer, 2 megawatt demand on the grid to supply them with hydrogen. And they have been quoted €250,000 approximately to put the feed in, and the electrolyzer station is another €8 million. So, so they've decided to look around for some other possibility. So I came up with the idea of looking at some very old chemistry, which is the production of hydrogen from aluminium, right? Which is very simple. I'm sure that quite a few people here have done it using aluminium, perhaps powder or bits of aluminium, and caustic soda, sodium hydroxide, and this produces hydrogen. And also, if you've done it, you will notice it produces a lot of heat. It's a very exothermic chemical reaction. And I thought, well, this is interesting. And I started looking at the hydrogen production. And then I realized, A, that sodium hydroxide is not the best catalyst. There are better. And also, the other problem is that the end product of turning that aluminium into another product and releasing the hydrogen is something called sodium aluminate, which is not a very useful chemical at all. It's used a little bit for dyeing clothing, for colouring clothes and so on, but it has a very small amount of use. Whereas if you use a different catalyst and you organise the chemistry carefully, then you make hydrogen and aluminium trihydroxide. And aluminium trihydroxide, also known as just plain aluminium hydroxide, Al2OH3, is a very valuable compound. And the economics are riveting, because if you buy 1 ton of... I use this kind of... I'll just show you something. This is the kind of aluminium that I like to use in this process. And this is not... it's this stuff. And you can see this is machine waste from... Actually, this came from the Aston Martin factory in England, where they machine aluminium engines. And this is very difficult to smelt. It's very difficult to recycle as metal. For a start, you can only put material like this into a cold furnace, because if you try and put it into a hot furnace, then it just all just flies up in the air like that. It's very, very difficult. And also they have to add a lot of sodium fluoride fluxes and salt and so on, and the yield of the yield of metal from this is around about 70%, and there is possibly, well, many, many tons produced by smelting this material of something called salt cake, which is a very noxious slag product, which there's a place in England where there is a small valley which is full of salt cake. They reckon it's got 10 to 15,000 tons of this aluminium slag, salt cake slag. And when it rains, you cannot even go anywhere near it because it gives off ammonia and hydrogen. It's very dangerous. It's become very dangerous. It has a big fence around it now. So there are clean ways of doing this. And in the laboratory, having worked on the catalysis, I built a plant, which as far as I know is the biggest one of its kind in the world. Toshiba built one, but theirs is a 5-litre system. And this is a 25-litre system. And this machine here will produce round about 3 kilos of aluminium a day. But the magic is, you get that 1 ton of scrap aluminium, it makes you about 110 kilos of hydrogen, so an 11% yield. But at the end of the process, you have 2.9 tons of aluminium hydroxide, which is worth probably 5 times as much as the scrap metal that you put in at the beginning. And all you've added to it is water. Yeah, so it's a bit like baking bread. You know, the baker buys a bag of flour that maybe weighs 50 kilos, and he turns it into 200 kilos worth of loaves by adding water. I do just the same. I add water to the aluminium, make it into hydroxide, and the answer is a very green. The hydrogen is incredibly pure. I've run samples of this hydrogen through a mass spectrometer, and the impurities are very low. It's perfect for fuel cells. It's perfect for almost any use, in fact. The impurities are measured in just a few parts per million, and there's nothing nasty in there. No carbon monoxide, no sulfur, no sulfides, and so on. So it's a good product. Now, here we are. So this is a little bit about the history of the company, which is not necessarily interesting. It's always been important to us, by the way. Just look at the last sentence there. Every part of our work is designed to be as green as possible. In other words, I'm only interested in doing chemistry that doesn't produce any toxic byproducts, that produces useful commercial items and adds value. It's based on the upcycling of materials. You take something like this, which is pretty useless, and you turn it into something very useful. The kind of thing you could drive your car, you could power your car with, or power a lorry. There is much debate, actually, about the best way to run this economy. Should we be using battery vehicles, or should we be using hydrogen vehicles? There is a place for both. Batteries are very good for cars and small vehicles. But when you get to a big lorry, a 40-ton lorry, then it will probably need something like 5 or 6 tons of battery. And I'll overlook the fact that nobody really knows how to recycle a battery, the fact that they would also need charging from the grid, and so on. It's not practical. The freight hauliers, the garbage companies, the waste collectors, they don't want to be running vehicles with 6 tons of dead weight on board. So hydrogen is good for heavy vehicles, batteries are good for cars. That seems to be how it is. There you are. There's a little about that argument there, yeah. So hydrogen fuel cells, of course, are not necessarily going to end up any more expensive than batteries, and they use much less in terms of precious raw material. There is a shortage of materials to manufacture fuel cells at the moment. The membranes are in very short supply. But, of course, as there is demand, those supply problems are overcome. And it says, as I say here, fleet operators, they need something where they can refuel their lorries quite soon. In other words, they're not connected to a charger for 24 hours and off the road. They need something faster than a battery system. And the whole fuel cell and electric drivetrain in a heavy truck weighs something like 700 or 800 kilos, compared with maybe 6,000 kilos for a battery truck. It's a huge difference, and that difference is profitability for the carrier. So what I've been working on designing is what I call the hydrogen pod, the H2 pod. Because it's an off-grid system, the power demand to produce hydrogen is very low. The process is very exothermic, and so it produces a lot of heat. A ton of aluminium produces 4 megawatt hours of potential hydrogen energy. So that 110 kilos is worth 4 megawatt hours. But it also produces 4 megawatt hours of process heat, of exothermic heat from the reaction. So there is a good possibility to use this in district heating schemes and so on. And I must emphasize this again, it makes no demand on the grid, because the grid, if Europe were to switch over to hydrogen, there are a few problems. It would require 2 terawatts of generation capacity to make all the hydrogen that Europe needs. Now, a terawatt, well, you may not be clear in your head what a terawatt is. It's a big number. But the entire world production of electricity at the moment is around about 15 terawatts. So for Europe to add another 2, you can imagine how big a project that would be. So it's not really going to happen. There's some information there, I'm sure. I managed to read the Italian quite well. Perhaps you can read the English. Okay, I hope. So hydrogen can be produced at the point of demand. If you have a truck depot, it doesn't matter where it is. It could be, you know, it could be in a little town in the middle of Umbria. It could be a small market town in central France. It could be anywhere. And because Coca-Cola supply the fuel for this system, yeah, and they distribute it all over the world for nothing. It's free. Yeah, you can pick it up in the street. Now, to go on from there, it's a little bit about how it works. I'd forgotten that slide was there. Never mind. You're welcome to read that. There is nothing revolutionary about the chemistry. It's a simple trick, but I just learned how to do it very well indeed, so that the products that come from it are very pure. And I've discovered a lot about hydrogen chemistry and particularly a lot about aluminium chemistry in doing it, because aluminium is a very versatile material. Yeah, there's lots of things you can do with aluminium, I've discovered. Because this process produces hydrogen and exothermy, you can imagine that if you were to take a sealed reactor and run this chemistry inside a sealed reactor, the temperature will go very high. And in fact, it does. I've done it. So the temperature will go up to around about 270 in the system I have. I can get the temperature up to 270 centigrade and round about 15 bar. So the reactor is full of a mixture of steam and hydrogen. And of course, with that mixture, you could run a turbine, yeah, a rotary engine, and extract the energy, the kinetic energy from the steam. But after you've done that, you've still got the hydrogen, which you can use for anything you want. You could use it to make more steam if you like to run the turbine. So you can actually achieve, theoretically, it looks like you can do cogeneration using this chemistry at round about 65 or 70% efficiency, which is remarkable. It's as good as a Brayton circle, a combined phase turbine, the very best systems that we've got. And as I say, it's everywhere. There are 1 billion tons of aluminium in the world. And that's all the aluminium there is, in cars, in windows, in cans, in foil for cooking, everything. 1 billion tons. America's official figure for landfilled aluminium, and a lot of it is this low value stuff that this chemistry is so good for, 2.4 million tons a year. In the EU, 27 countries, the figure is much the same. So between the EU and the USA, we are at the moment landfilling 5 million tons of aluminium metal, all of which could be used to make hydrogen. And more importantly, could be made to use aluminium hydroxide, made to make aluminium hydroxide and aluminium oxide. To make aluminium hydroxide, the raw material, the first raw material for manufacturing metallic aluminium, requires the mining of bauxite and bauxite clay, and it's mined in Europe. It's mined these days mostly in the Gulf and in China and Australia, and it's a very dirty business to extract or refine, as they call it, to refine the hydroxide using something called the Bayer process. It requires large amounts of sodium hydroxide, steam heat, and so on. It's very polluting, and even the best grades of bauxite clay only have about 50% of aluminium hydroxide in them. Now, that residue from that process, the toxic sludge, if you like, which is called red mud, is currently around about 150 million tons a year of red mud are being produced. And there are people who've worked on things you can do with it, different products you can make. But the problem is it's being produced in places where they have no capacity to recycle it. Fabrice was telling me yesterday about a place in France where they've been dumping it in the sea. There's a place in Italy. There's an Italian bauxite business has been dumping it in the Mediterranean, in a bay in the Mediterranean for many years. I think they've stopped production at the moment. But nevertheless, you see what's going on. So if that 5 million tons of landfilled aluminium that I talked about in America and here was used to make aluminium hydroxide, not only would you have 500,000 tons of hydrogen, right, which is a lot of hydrogen, and a huge amount of process heat, which could be used for all kinds of stuff, you would have, at the end of that, 15 million tons of aluminium hydroxide, right, which would prevent the mining of 30 million tons of bauxite clay. And the shipping around the world, it just goes on, yes. And also prevent the production of something like 20 million tons of CO2, of carbon dioxide. 20 million tons. Yes?
5 minutes.
Okay. Oh, thank you. Okay. I'll get on with it. Sorry, you've got me on my favourite topic at the moment here. I'm hard to stop. Okay, this is just a little view of how it might work in the circular economy. You see there's people at the top left here. You've got people producing waste, and it goes to a collection point. It gets processed in the H2 pod, and then it makes heat, it makes hydrogen, and also it makes stuff that can be cleanly recycled back into aluminium, back into metallic aluminium. So it's not lost. And this is what I call the non-preferred aluminium, the stuff nobody wants. This just tells you what it's unique about it, but I've already told you that, so we'll go on. So there you are, you see the emphasis on modular. In other words, you can build this machine any size, that you can put it anywhere you like. All you need is some clean water and a very small electricity supply, maybe 20 or 30 kilowatts, not 2 or 3 megawatts, just 20 or 30 kilowatts will run a big plant. And of course, the plant has the ability to make its own energy when it's running. So it's very small infrastructure requirement. It produces, if you run it with a fuel cell, it produces a lot of sterile hot water as well. Clean, sterile hot water from the fuel cell, which in some places will be very valuable indeed, especially for things like disaster relief and so on. But I don't know much about that business, the disaster relief, that is. So at the moment, we have characterized the process. We have developed paper designs for a big plant, and we are looking at things like the grid. We're looking at the scrap metal industry, the people who collect the aluminium. We are talking to a couple of I'm talking to a company in Austria who are very interested in building this plant. And it seems that the more people understand about the aluminium industry, the more interested they are in this process, because they realize that it fills a gap, it fills a niche in the business. And so right now I'm trying to raise I don't know, 3-4 million euros to build the first big plant. And maybe this year that will begin. I hope so, I hope so. But I think I've said enough. I'm very happy this is just about money. There you are. And it's a very profitable business, by the way. I've had a good accountant looking at the figures, and it is his opinion that the return on investment, in other words, if you spend 4 million euros building a plant, how long does it take to get the 4 million euros back? The answer is less than 2 years. Yeah, so the return on investment is very high. There we go. And we're looking at routes to market. The biggest obstacle at the moment is the nature of the whole business, in that the people who produce the scrap metal, the people who collect the scrap metal, the aluminium, are mostly, some are big companies like Suez, but there are lots of relatively small businesses who you can talk to. At the moment, aluminium hydroxide and aluminium oxide are produced by huge global companies like Rio Tinto Zinc, like Iveris, and so on. And I've managed to get a route to talk to somebody in Iveris, which is a global company. They employ, I think, 15,000 people. They have a bauxite business and so on. They get it. They're interested. But to talk to somebody at Rio Tinto Zinc about something that disrupts their current business model, impossible. Absolutely impossible. And I've tried talking to Coca-Cola. Coca-Cola are not remotely interested in recycling. Not remotely. They have a director of sustainability. His job is to talk about sustainability, not to do anything about it. I've been right to the top in Savannah, Georgia, the HQ of Coca-Cola worldwide. Impossible. They're just not interested. They want to talk the talk, but they don't want to walk the walk. This is a little overview of the process. It's just a block diagram showing what goes on. And it shows 10 tons of input, and at the other end, if I remember correctly, and I certainly can't read it from here, it shows you how much of the hydroxide and the heat and so on comes out of it. Yeah. So the hydroxide that this makes, by the way, is very interesting. It is a very fine, uniform crystal structure, 3 to 5 microns in size. And the crystals themselves are very crisp, very sharp, and apparently good for catalysts. Okay, I think we're there. If I say it's sustainable, you have to believe me. Are there any questions? If we have a moment for questions? We do? Yes. Okay.
We have time for questions.
Francesca.
I just have one curiosity. I lost, what is the electrolyte you use to avoid the formation of aluminum sodium compound?
There is no electrolyte because there is no electricity. It's a purely chemical reaction.
I see.
And the catalyst is a secret.
It's a secret.
It's a mixture.
But
it's a mixture.
The second question is, okay, I have a very short question. During the process to produce hydrogen, you need to have some energy. Is it right?
A very small amount at the beginning. If you just put everything into a reactor or a bucket or whatever and leave it, then the reaction will begin, but very slow. If you raise the temperature initially to about 65 centigrade, then the reaction becomes very fast. It's very rate dependent, yeah? You reach 65 and it goes like that. And so there's a very small amount.
Okay.
Typically, to make that 3 tons of hydrogen, 3 kilos of hydrogen, which is worth something like, has a potential energy of 120 kilowatts. The system in my lab, we use 5 or 6 kilowatt hours to do that. So the COP is 20. In a big plant, 50 or 60.
Okay, thank you.
Okay, sorry, Francesca, yes.
I will understand that your catalyst is a secret, obviously, your catalyst.
Yes.
But there is some problems for the recycling the catalyst.
Of recovering it?
Recycling the catalyst can be some...
Oh, sure. I don't think it will survive modern examination. No, of course not. I can never keep it a secret for very long. Right now, I don't want to talk about it too much, but I do understand that if we build a plant within 12 months, then somebody else will be wanting to do it too. So it's the old story. Be first, be fastest, be the best, and run good customer service, Francesco. Answer questions immediately.
Okay, thank you.
Other questions? No.
I do actually I have filed patents for the plant, also for cogeneration, the high pressure system I talked about. I've filing patents, also filed a patent for the zero CO2 manufacture of aluminium oxide, which is calcined, in other words, very strongly heated in a furnace, aluminium hydroxide. So you use the aluminium to make aluminium hydroxide and use the hydrogen to transform that into aluminium oxide. That's a patentable process. And the other one is the idea, I'm currently writing a patent for the idea that a waste company who does smelting, somebody who runs a smelter, for example, to remelt aluminium, could use this very bad and boring part of their inlet stream, the least profitable, the most polluting, the most difficult as far as they're concerned. They could use that 20% or so of their input stream of raw material to make hydrogen, to smelt the rest, and then sell the hydroxide at a profit. So suddenly they're not buying methane from the grid to run their furnace. They're using the raw material that they're buying, and they're selling the end product, which is this stuff, by the way. I got this through customs, okay? They're very lax at the moment. Customs, all this white powder, I just got it through customs. They never even asked me. And that's the end product. This is clean hydroxide. Yes?
Go on.
If you produce some pollution of dioxin or some
No, not at all.
no poison.
Nothing. No